NCA-GenL is NVIDIA's Associate certification for generative AI and large language models, and I am here to get you exam ready. You get the foundation the exam is built on, the traps that quietly cost people points, and a study routine that tells you when you are actually ready. And if you want the full study guide, hands-on GPU-powered labs, and practice tests for NCA-GenL, check out the NCA-GenL page on preparado.com. The link is in the description. Let's go. Picture yourself at your own desk, webcam on, a remote proctor watching, and a 60-minute clock quietly counting down. That is the NCA-GenL, NVIDIA's associate-level exam, which means it assumes only a basic grasp of generative AI with no formal prerequisites. In that single hour, you answer 50 to 60 multiple-choice questions, all online. It runs about $125. And NVIDIA does not publish an official passing score, so your job is simply to answer confidently across every topic. Every question is drawn from 5 knowledge domains, from core model fundamentals to trustworthy deployment. Let's map those 5 out next. Imagine you type one question into a chat box, and a paragraph comes back that actually answers you. Everything the NCA-GenL exam tests lives on the path that question takes. So before we go domain by domain, let me draw you the whole map. That journey from your prompt to a useful answer is the exam. Your prompt first gets broken into tokens, which are the small chunks of text, roughly word fragments, that the model actually reads. Those tokens feed a large language model, and at its heart is a transformer, the neural network architecture that weighs how every token relates to every other one, and then predicts the next token, over and over, to build the reply. On its own, the model only knows what it saw in training, so we extend it. Retrieval fetches relevant documents and pastes them into the prompt, so the answer stays current and grounded. And tools let the model call out to a search engine, a database, or your own code when it needs to act. Then the whole thing has to be served to real users, which means paying attention to latency, throughput, and cost. And because people rely on the output, it has to be trustworthy, which covers safety, privacy, and defending against attacks like prompt injection. NVIDIA splits that map into 5 domains, and the ring drawing on now is how much each one weighs. Core machine learning and AI fundamentals is the biggest at 28%. Data and experimentation is 22%. LLM software development is 20%. Prompt engineering and alignment is 18%. And deployment and trustworthy AI is 12%. Those 5 segments are the rest of this video. So let us start where the weight is. Imagine you type the sentence, "The cat sat on the," into a chat box, and the model instantly suggests Matt. That single act, predicting the next piece of text from everything that came before it, is the entire job of a large language model. An LLM is a neural network, meaning a large stack of numeric layers whose internal weights were tuned on enormous amounts of text. And all it fundamentally does is estimate the most likely next token given the tokens it has seen so far. Training is how those weights get set. The model reads billions of examples, guesses the next token, checks how wrong it was against the real next token, and nudges every weight a little to be less wrong next time, repeating that until its predictions sharpen. A token, by the way, is not quite a word. Tokenizers split text into subword pieces. So a common word like cat is one token, while a rarer word gets broken into several, which is why the exam counts tokens, not words. Each token is then convoluted into an embedding, a dense list of numbers, a vector, that places tokens with similar meaning near each other in space, so king and queen sit close together. Those embeddings flow into the transformer, the architecture behind every modern LLM, and its core trick is self-attention. Every token looks at every other token and decides how much each one matters for understanding it. Picture the phrase, "the bank of the river." Attention lets the word bank look at river and settle on the water meaning rather than the money one. And that is exactly the relationship the exam asks you to name. Mechanically, attention multiplies query and key vectors to score how related two tokens are, scales those scores down, and runs them through softmax, a function that turns a row of raw numbers into probabilities that add up to 1. At the output, the model produces a probability for every token in its vocabulary, picks one, feeds it back in, and repeats, generating one token at a time. The context window is the maximum number of tokens it can hold in view at once, and anything older than that limit simply falls out of sight. Two sampling knobs steer the choice. Temperature controls how random it is, with higher values more creative, and top P keeps only the smallest set of top tokens whose probabilities add up to P. One last distinction the exam loves. Pre-training is the expensive first pass, where the model learns language in general from raw text, while fine-tuning is a cheaper second pass that adapts that base model to a specific task or style on a much smaller dataset. Get comfortable with the flow from tokens to embeddings to attention to next token prediction, and Domain 1 is yours. Domain 2, Prompt Engineering and Alignment, 18%. Imagine you ask a model to sort customer emails, and you write, "Help me with these," and it hands back a friendly paragraph instead of doing anything useful. The same model, given a sharper prompt, will nail the task cleanly. And this whole domain is about why the wording is the work. A zero-shot prompt just states the task and trusts the model to figure it out from what it already learned during pre-training. A few-shot prompt hands it 2 or 3 worked examples first, so the pattern is unmistakable. And for anything with a specific output format, few-shot almost always beats hoping the model guesses your intent. When a problem needs genuine reasoning, like a multi-step math word problem, you add chain of thought, which simply asks the model to show its work step by step before committing to a final answer. That extra scratch space measurably raises accuracy, because the model reasons through the middle instead of blurting out the end. 2 more levers the exam loves. A system prompt sets the standing rules in persona for the entire conversation, separate from each user message. So you say, "You are a precise SQL assistant" once, and it holds throughout. And when your code has to read the reply, you request structured output, meaning valid JSON with named fields, so a program can parse the answer instead of scraping loose prose. Now, alignment. A raw pre-trained model only predicts the next likely token, so it is not naturally helpful or safe. Instruction tuning fine-tunes it on thousands of instruction and response pairs until it reliably follows directions. And then RLHF, reinforcement learning from human feedback, trains it on human preference rankings to be helpful, harmless, and honest. Constitutional AI is a related approach that uses a written set of principles to guide that behavior. The exam pairs alignment with hallucination, which is when a model states something plausible sounding, but flatly untrue. You reduce it by grounding the model in retrieved documents through RAG, and you add guardrails, the safety filters that block unsafe prompts and unsafe outputs. Sharp prompts, alignment, and grounding together are how you earn answers you can actually trust. Imagine you have scraped 1 million forum posts to fine-tune a model, and half of them are HTML tags, duplicate threads, and broken Unicode. The model does not see your good intentions. It only sees the bytes you feed it. So garbage in stays garbage in. Domain 3, data and experimentation, is 22% of the exam, and it starts before any training runs, in the pipeline that cleans and shapes the data. That pipeline has a few named stages the exam expects you to know. Pre-processing strips the noise, removing markup, normalizing white space and casing, and filtering junk. Tokenization then splits the clean text into tokens, the subword units a model actually reads, usually with byte pair encoding, which starts from characters and merges the most frequent pairs into a working vocabulary. Feature engineering is the older world step of hand-building input signals, and for language models, embeddings mostly replace it, since the learned vectors already carry meaning. Before you trust any result, you split the data into 3 parts. You train on the training set, you tune your choices against a separate validation set, and you touch the test set exactly once, at the very end, as an honest final grade. This discipline exists to catch overfitting, which is when a model memorizes the training examples instead of learning the pattern behind them. It looks brilliant on data it has already seen, and then falls apart the moment a real user types something new. You spot it on a simple curve, training accuracy climbing toward perfect, while validation accuracy stalls and then drops. The widening gap between those 2 lines is the signature of a model that stopped generalizing. Then you have to measure quality with the right metric, and the exam loves testing whether you pick the right one. For classification, accuracy is fine on balanced data, but when one class is rare, you reach for precision, which asks how many of your positive calls were correct, and recall, which asks how many real positives you actually caught. F1 is their harmonic mean when you need one balanced number. For a language model itself, perplexity measures how surprised it is by real text, and lower is better. For generated text, Rouge scores summaries by overlap with a reference, and Blue does the same job for translation. Wrapping the whole thing is experiment design. You change one variable at a time, hold everything else fixed, and compare against a baseline so you can prove the improvement came from your change and not from luck. That is the entire domain, running data through a clean pipeline and judging it with an honest metric. Imagine you are building a support chatbot that has to answer questions about your company's own docs, which the model has never seen. Domain 4, LLM software development, 20%, is about the Python code that wires a language model into a working app. You will lean on 3 libraries by name: Hugging Face transformers to load and run models, and LangChain or Llama Index to orchestrate the steps around them. The catch is that your docs live as plain text, and the model needs to find the relevant passage fast. An embedding solves this. It turns a chunk of text into a dense vector, a list of numbers that captures its meaning, so 2 passages about the same idea land near each other in that space. A vector database stores those vectors, and at query time, you embed the question and pull the nearest chunks by cosine similarity, which measures how close 2 vectors point in meaning, rather than matching exact words. That pattern is retrieval augmented generation, RAG, and it runs in 5 steps you should be able to draw from memory. First, you chunk the documents into small passages. Second, you embed each chunk into a vector and store it. Third, when a question arrives, you retrieve the closest chunks. Fourth, you augment the prompt by pasting those chunks in as context. Fifth, the model generates its answer, grounded in that retrieved text. This is why RAG is the standard fix for hallucination, where a model states something plausible but false. Instead of trusting the weights to remember your docs, you hand the model the real passage and ask it to answer from that, so the source is right there in the context window. Around that core, you build the app itself. A chat app keeps conversation history and feeds it back each turn, and an agent goes further by letting the model call tools, meaning it decides to run a search or hit an API and then continues with the result. LangChain and Llama Index give you the plumbing to chain these calls, one step's output feeding the next. All of it reaches the model through an API and its SDK, and 2 calling patterns show up on the exam. Streaming sends tokens as they are generated, so the user sees the answer appear rather than waiting for the whole thing, which cuts perceived latency. Asynchronous calls let your program fire off a request and keep working instead of blocking, which is how one server handles many users at once. Imagine your model works beautifully in a notebook on your laptop, and then 1,000 users hit it at the same time. Domain 5, Deployment and Trustworthy AI, is the smallest slice of NCA-GenL at roughly 12%, and it covers everything that happens after the model is trained: how you serve it, how you keep it fast and affordable, and how you keep it safe. Serving means wrapping the model behind an API so applications can send it requests and get answers back. On the exam, NVIDIA's own tools show up here. NIM packages a model as an optimized microservice inside a Docker container with a standard API, so you deploy it without hand-building the runtime. And Triton is the inference server that runs models from many frameworks at once. Every serving decision pulls on 3 levers. Latency is how long one user waits for a response. Throughput is how many requests you handle per second. And cost is the GPU bill underneath both. Techniques like dynamic batching, which groups incoming requests together, and quantization, which stores the model in lower precision numbers, buy you throughput and lower cost, usually by trading away a little latency or accuracy. Shipping the model is not the end. Monitoring and observability mean watching latency, error rates, and output quality in production, because models drift as the real world changes, and a system that was accurate at launch can quietly degrade. Then there is the trustworthy half, and this is a checklist worth memorizing. Bias, where the model reflects skew in its training data. Safety, keeping it from producing harmful output. Privacy, protecting personal information, or PII, that users type in. Security, defending against prompt injection, where an attacker hides instructions inside the input to hijack the model. And licensing, knowing what you are actually allowed to do with a model and its data. The exam treats these as the difference between a demo and a real product. So when a question asks the responsible move, it is almost always the one that protects the user. Picture the exam not as 60 random questions, but as the same 4 shapes wearing different costumes. Once you can name the shape a question is testing, you already know where the answer lives. The first shape is pick the best tool. A scenario describes a need, like grounding answers in a private document set, and asks what you would reach for. Match the job to the tool. Retrieval augmented generation for fresh external facts, fine-tuning for a fixed style or format, and a plain prompt when the base model already knows enough. The second shape is choose the right metric. When a question asks how you would measure a summarizer, accuracy is the wrong tool, and rouge or blue, which compare generated text against a reference, is the right one. Perplexity judges a language model, and precision, recall, and F1 judge a classifier. The third shape is debug the pipeline. The model returns something wrong, and you have to find where it broke. Walk the RAG pipeline backward. Bad output often traces to bad retrieval, and bad retrieval often traces to chunking or embeddings, not the model itself. The fourth shape is the safety and trade-off judgment call, weighing latency against cost or blocking prompt injection without breaking real users. There is rarely a free win, so the best answer names the trade-off instead of pretending it away. Name the shape first, and the 4 options stop looking equally tempting. Give this 3 weeks, and the whole thing gets manageable. Every resource you need already lives on preparatum.com, and each week runs the same rhythm. You read the domain guide for the theory, you drill the concepts until recall is automatic, and you close with a practice test that tells you exactly what is still leaking. The domain weights decide where your hours go, so heavier domains earn more of your week. Week 1 is the foundation. Core ML and AI fundamentals at 28%, paired with prompt engineering at 18%. Spend the first 3 days walking the transformer pipeline until you can draw it from memory. Tokenization into embeddings, self-attention, softmax, and next token prediction, plus context windows and the temperature and top P sampling knobs. Then give the back half of the week to prompting patterns, zero shot and few shot and chain of thought, and finish with the Domain 1 and Domain 2 quizzes. Week 2 is where you get practical. Data and experimentation at 22%, alongside LLM software development at 20%. Learn the metrics cold, accuracy and precision and recall and F1, plus perplexity and blue and rouge, and be able to spot overfitting on a train versus validation curve. Then build the RAG pipeline in your head and in code, chunk to embed to retrieve to augment to generate, and take the midpoint practice test to see the 2 new domains land. Week 3 closes the gap. Start with deployment and trustworthy AI at 12%, the lightest domain, covering serving basics like NVIDIA NIM and Triton, the latency, throughput, and cost trade-offs, and the responsible AI checklist of bias, privacy, and prompt injection. That takes 2 days, which frees the rest of the week for full-length timed practice exams under real conditions. After each full test, do not just read the score. Mine the misses. Every wrong answer points at 1 domain guide to reread and 1 quiz to re-drill. And that targeted review is what moves you from passing to comfortable. Do this loop until your practice scores hold above the pass line 2 exams in a row, and you walk in ready. Most questions you will miss on this exam are not about what you know. They are about a trap in the wording. So learn to delete 2 answers before you ever pick the right one. First, the absolute trap. Any option that says a technique always works, never fails, or is the only correct choice. Generative AI lives on trade-offs, so a sentence that leaves no room for a trade-off is almost always the wrong one. Second, right tool for the wrong job. The option names a real technique that solves a different problem than the one asked for. When a question wants fresh, factual answers, fine-tuning is a genuine method, but retrieval-augmented generation, feeding the model live documents at query time, is the one they are testing. Third, plausible but outdated. An answer that was best practice a few model generations ago and reads comfortable today. Tiny context windows, word count token math, and bag of words embeddings all sound reasonable, and all belong to an earlier era. Fourth, over-engineering. The option that stacks fine-tuning, a new pipeline, and a custom model when a clear system prompt or 1 retrieval step would do. NVIDIA grades the simplest option that fully solves the problem, so reach for the heavy machinery only when the question forces it. Read every option first. Delete the absolutes, delete the outdated, and you will be choosing between 2 real answers on almost every question instead of 5. So here is the whole exam in one breath. The transformer and sampling knobs in Core ML and AI fundamentals, the prompt patterns and alignment loop in prompt engineering, the splits and metrics of data and experimentation, the RAG stack in LLM software development, and serving with responsible AI in deployment and trustworthy AI. 5 domains, and every one of them is something you can actually reason through once you have seen how the pieces connect. Now go turn that understanding into reps. Run the practice questions on Preparado.com until every domain feels routine. Then walk in and pass it.